So we'll start once again. We have been talking about structural characterization, and in the structural characterization we talked about symmetry in the last class. We said symmetry is usually defined in terms of two aspects. One is called the rotational symmetry and another is called the translational symmetry. So if you define in this fashion, we say there are two types of materials, which are crystals and another amorphous. Crystals are those which has both rotational and translational symmetry, and amorphous are those which do not have. And among the crystals there is a subset which is called a quasi-crystals, which have rotational symmetry, certain special rotational symmetries which are, for example, five-fold symmetry, but they do not have the normal translation symmetry, but they have a special type of translation symmetry which we call it as a quasi-periodic symmetry. So whereas crystals, normal crystals are periodic, whereas quasi-crystals are quasi-periodic. So this is what we have talked in the last class, and now we will go to the crystals and keeping these special type of crystals aside, and we will talk more about what are called the normal crystals, which are more popular, and try to know more about these crystals. For example, the crystals are usually, if you look at a crystal structure, the crystal structure is something which we usually define as that which has a long range periodicity. Okay, so when you take a long range periodicity, people have seen that there are 7 ways of arranging atoms, which are now people define them as 7 crystal systems. And when people looked at how do you arrange atoms and what are the maximum possible combinations by which I can arrange atoms, people have come across 7. And now it is accepted that there cannot be anything beyond these 7 crystal systems, and these systems are usually called cubic, that is 1, second tetragonal, third what is called orthorhombic, fourth is what is called rhombohedral, fifth is hexagonal, sixth is monoclinic, and seventh is triclinic. These are all the 7 systems that people have come across. And if I define a basic building block for a crystal structure, that building block is usually called as a unit cell. And this unit cell, because that is the unit which is building the whole structure, if I take a unit cell and translate that unit cell in all the x, y and z, all the 3 directions, then I get a crystal structure. So a crystal structure is composed of a unit cell which is the building block, and this building block, if I draw any such building block, just for a sake of understanding, you can say that this building block has 3 axes, one here, one here, one here. And usually people call them as A, B, C. And the angles between each of them, for example, the angle between A and B is called gamma. The angle between B and C is called alpha. The angle between A and C is called beta. So there are 3 axes and 3 angles which define the whole unit cell. These are called 6 lattice parameters. When we say lattice parameter, it is not simply the length of this axis, but also the angles. So in principle you need 6 parameters to define a unit cell. But among these 7 crystal systems, there are certain systems with certain relations between these 6 lattice parameters. And that when we look at it, we see that A cubic is one where A is equal to B and it is equal to C, and alpha equal to beta equal to gamma equal to 90 degrees. As a result, in principle, in a cubic system, I need to only define 1 lattice parameter. That is simply A. For example, if I tell about what is the length of this, I need not have to tell the length of this and length of this because they are all equal. And I know that all angles are 90 degrees. So I do not need to define. So 1 lattice parameter is enough to define a cubic. Similarly, when you come to tetragonal, we say A equal to B but not equal to C. Whereas all these angles are equal and 90 degrees. That means what? I need to define here A and C. two parameters have to be, because A and B are equal, so I do not need to define both of them, I need to define only one of them. So I need to know about two lattice parameters. When I come to orthorhombic, I know A is not equal to B and it is not equal to C, and all the angles are equal to 90 degrees. And so, because A is not equal to B and not equal to C, I need to define three lattice parameters. And in fact, it is easy to find out how these two come up, about from a cubic. If I take a cube, for example, I do not have any cube here, but if I take a cube and let's say imagine that this is a cube and pull it along the C-axis, what happens to it? It simply, the C-axis gets elongated, A and B do not change and the angles also do not change if my pull is such that. Then what happens is cubic becomes tetragonal. Simply just by pulling it or compressing it along the C-axis, I am converting a cube to a tetragonal. Similarly, if my pull is in two directions, both C direction and B direction or A direction, and I can think of an orthorhombic coming out, where angles are not disturbed. And then when you come to a rhombohedron, rhombohedron is a special case where A is equal to B equal to C, and alpha is equal to beta is equal to gamma, but they are not equal to 90 degrees. This is not equal to 90 degrees. That means what? If I can again talk about how do I get rhombohedron from a cube. Take a rhombohedron from a cube and then pull it along a body diagonal. If I pull it along the body diagonal, what happens is all the angles will no longer remain 90 degrees. They get changed and they become some angle which is other than 90 degrees, but A and B and C will be equal, and that is what is a rhombohedron. And that means what? I need to talk about one length axis, length dimension, and I need to give one of the angle. Because if I tell what is alpha, I know what is beta, what is gamma. But I know definitely that all of them are not 90 degrees. So that means I need to define two lattice parameters here. And when I come to hexagonal, hexagonal is a special type of symmetry where it has A equal to B but not equal to C, and alpha equal to gamma, which is equal to 120. If I look at it, alpha and alpha and beta are 90 degrees, whereas gamma is 120 degree. This angle is 120 degree, whereas these two angles are 90 degrees. The angle that the C-axis makes with A and B are 90 degrees, whereas the angle between A and B is 120. That is the special type of symmetry. And this also, because all the angles are known, I don't need to define the angles, but I need to define A and C. So that means again here also I need to talk about two lattice parameters. When I come to monoclinic, monoclinic is a situation where A is not equal to B, it is not equal to C, and here alpha equal to gamma, and it alpha, only one of the angle is 90 degrees. Alpha is not equal to gamma, not equal to gamma, but beta is a special angle which is 90 degrees. One of the angle is 90 degrees. A very special case, and rest of the angles are not equal to 90 degrees. So I need to talk about three axes and two angles. So I need to define five lattice parameters here. Only one angle is known to me. Rest of the things are not known to me. And if I go to triclinic, it's one of the worst symmetries where alpha is not equal to beta, is not equal to gamma, is not equal to 90 degrees. All of them are not equal. So that means I need to define three axes and three angles. So total 6 I have to define. This is how people have said that there are 7 systems. But in principle, this is not the best way to define a system. The best way to define a system is in terms of its symmetry. Let's look at the symmetry of a cube. For example, if I look at cube, I said earlier that the square has a 4-fold symmetry, right? If I look at a cube, what are the symmetries of a cube? And carefully look at this cube. This cube is made up of squares, right? This is a square. Okay, so this is a square. This square has a For example, a 4-fold symmetry. But 4-fold symmetry is not only there in this square, but also there in this square. It also is there in this square. Right? So this is also a 4-fold symmetry, this is also a 4-fold symmetry, this is also a 4-fold symmetry. That means all the x-axis, y-axis, z-axis, all the three are 4-fold symmetries. That means what? A cube has 3 4-fold symmetries. 3 mutually perpendicular 4-fold symmetries. This axis is perpendicular to this axis and this is perpendicular. So 3 mutually perpendicular 4-fold symmetries. This is characteristic of a cube. Whereas a square has only one 4-fold symmetry because it is only a 2D. And now, does it have anything else? If I want to know that, let me look at this plane. This plane, which is a triangular plane, which is touching the 3 corners of this, is a special plane. It's a triangle, no doubt, but it is not just a normal triangle. If you carefully look at it, this is equal to this is equal to this. That means it's an equilateral triangle. Because all these 3 are nothing but the diagonals of a face. And diagonals of the face are root 2a, we know, in a cube. So they are all root 2a. That means they are all equal. So that means it is an equilateral triangle. And an equilateral triangle, we know, has a special symmetry. It is called, it has a 3-fold symmetry. And how many such planes are there? I have actually 4 such planes. In principle, there are 8 planes, but certain planes are parallel to each other, so we do not. For example, if I look at this plane, what I just now showed you, and I take another plane, which is this plane. If you look at that plane and the previous plane, both are parallel to each other. They do not intersect. They are parallel to each other. You need to visualize. 3D is something which needs to be visualized. If you carefully visualize, these 2 are parallel to each other. And the axis which has a 3-fold symmetry is an axis which goes from this corner to this corner. This is the axis. And that is perpendicular to both these planes. And because they are 2 parallel planes, we do not consider them as 2 separate 3-fold axes, because there is only one axis which is perpendicular to both these planes. So we can see that there are 4 3-fold axes. Joining 2 corners, and I can join this corner with this corner, this corner with this corner, this corner with this corner. So out of the 8 corners, if I join all the opposite 2 corners, 8 become 4. 4 axes, 4 3-folds. So this is the characteristic of a cube. When we say cube, cube has a 3 4-fold symmetries and 4 3-fold symmetries. That is a cubic. Now if I come to tetragonal, tetragonal is what? Tetragonal is something like this, right? Now if I look at this tetragonal, how did I get tetragonal? By pulling the cube along the c-axis, I got a tetragonal. But by doing this, what is it? Does it have 3 4-fold axes? If I look at the 6 faces of a tetragonal, I see that this face is now a rectangle. It's no more a square. It is a square here, but it is not a square there. So how many such rectangles are there? There are 4 rectangles here. And are there any squares here? If I carefully observe, I see that there is a square on top, there is a square on bottom. That means there is only one axis, which is a c-axis, which is a 4-fold axis. The a-axis and the b-axis, which are perpendicular to this plane and this plane, they are not 4-fold symmetries. They are only 2-fold symmetry. One important thing that I need to tell you is, whenever I say there is a 4-fold symmetry, there is also a 2-fold symmetry inherent. For example, when I say square has a 4-fold symmetry, if I rotate 1, 2, 3, 4, if I rotate by 180 degrees, 1 goes to 3, 3 goes to 1, 4 goes to 2, 2 goes to 4. That means a square also has a 2-fold symmetry. But we do not say that. We only talk about the highest symmetry possible for a shape. Now if we look at the tetragonal, what is the highest symmetry possible? It has 1 4-fold symmetry. What is that 1 4-fold symmetry? It is the c-axis. But it also has a two-fold symmetry. The A axis and the B axis are two-fold, but we do not talk about it. When somebody asks, what is the characteristic symmetry of a tetragonal? We say it has one four-fold symmetry. What about three-fold? We said in cube there are 4 three-folds. How many three-folds are there in a tetragonal? Let us draw this plane. Now look at this plane. Is this an equilateral triangle? No. It is now an isosceles triangle. Once it is an isosceles triangle, it cannot have a three-fold symmetry. So that means there is no three-fold symmetry in tetragonal at all. By just pulling the cube along the C-axis, I have killed all the 4 three-folds. Not only 4 three-folds, I have killed 2 four-folds. Now you can see it has only a tetragonal crystal structure has only one four-fold symmetry. That's it. Now if I look like this to other things, you will see that if I start writing what are all the things that are there in each of them, you will see in tetragonal we have one four-fold. And if I come to orthorhombic, orthorhombic will not have any four-fold at all. Why? Because A is not equal to B, not equal to C. Unless A equal to B, and if the angle is 90 degrees, unless A equal to B, this equal to this, and if the angle is 90 degrees, then only you will see a four-fold symmetry. If the A equal to B, but the angle is not 90 degrees, then also you will not get a four-fold symmetry. So to get a four-fold symmetry, you need to have at least 2 axes to be equal, and the angle has to be 90 degrees between them. That is the reason why these two have four-fold symmetries. Orthorhombic does not have. But what does it have? Because all the 6 faces are rectangles, and rectangles have two-fold symmetries. So we can say it has 3 two-fold symmetries, right? Because all the 3 angles are 90 degrees. That means, so the rectangle, if I look at it, a rectangle has this not equal to this, but this angle is 90 degrees. Once the angle is 90 degrees, you get a two-fold symmetry. If the angle is not 90 degrees, then you don't get two-fold symmetry at all. In order to achieve a two-fold symmetry, you need to have at least one angle 90 degrees. And here, because all the 3 angles are 90 degrees, then you get 3 two-folds. All the 3 faces which are perpendicular to x-axis, y-axis and z-axis, they are all rectangles. Because they are all rectangles, you will see that you have these kind of 3 two-folds. Now when you come to rhombohedron, rhombohedron has 1 three-fold. That's it. Nothing else. Because all the angles are equal in rhombohedron. Okay? And all the sides are equal. But the angle is not 90. If the angle was 90, then you would have got a three-fold, two-fold or a four-fold. But because the angles are not 90, you cannot get either a two-fold or a four-fold. It has 1 three-fold. Now if I come to hexagonal, hexagonal is a special symmetry where you have what is called 1 6-fold symmetry. Whenever I say 6-fold symmetry, look at this hexagon. Assume this to be hexagon with all sides equal, and it has a 6-fold symmetry here. Because this is equal to this is equal to this, and all of them are equal. But if I carefully look at it, it also has a 3-fold symmetry. It also has a 2-fold symmetry. Because, for example, if I take this axis and rotate, if I say 1, 2, 3, 4, 5, 6, if I rotate by 120 degrees, this 1 goes to 3, 3 goes to 5. Rotating by 120 degrees. So you will see that this has also a 3-fold symmetry, but we will not talk about it because 3-fold is a subset of 6-fold. Just it does not, the vice versa is not true. Just because something has a 3-fold symmetry, it may not have a 6-fold symmetry. But if something has a 6-fold symmetry, it is bound to have a 3-fold symmetry. But we do not talk about it because it is inherent. Now if you come to monoclinic, it has only 1 2-fold symmetry. Why 1 2-fold? One of the angle is 90 degrees. But none of them are equal. If they were equal, then it would have had a 90 degree plus A equal to B would have brought a 4-fold symmetry. Because they are not equal and only one angle is 90 degrees, you will have 1 2-fold. That's it. And triclinic is something which has no symmetry at all. because none of the angles are equal, none of the sides are equal, no symmetry at all. So this is how you can talk about this, and in principle the best way to define the unit cells is not in terms of this, but in terms of this. This is how a crystallographer would like to define the crystal structures. And as a result, you would see that because of this, the arrangement, if you carefully look at it, the way they are arranged also is in that order. For example, cubic has the highest symmetry because it has 3/4 folds. Nothing else has that much symmetry. That is the reason why in periodic table, out of all the 100 or so elements, you will see most of them, at least 80% of them want to form cubic. Most of the crystal structures are cubic because of that. Atoms want to be arranged in the best fashion. Now this brings down to the next level, what is called, once I know the crystal systems, what about the unit cells? Are there any higher numbers possible? To understand this, for example, we say, for example, if I take a cube where you have one lattice point at each of the corner is called a primitive. Some people also call it a simple cubic. If I now add another lattice point at the center of the body, we call this as body-centered cubic. Instead of the lattice point at the body center, if I put a lattice point at all the face centers, then we call it as FCC, face-centered cubic. And why I'm using this term lattice point? In fact, now people call a crystal as lattice plus motif. I did not say the word that if I have an atom at the face centers, I only said lattice point at the face center. The reason I have to say this is only in case of, let's say, pure metals, we can say that there is an atom. For example, if I take an aluminum has an FCC structure. And in aluminum, every face-centered atom, face-centered position, you have one aluminum atom. And every corner you will have an aluminum atom. Whereas there can be some face-centered cubic, there can be some face-centered cubic structures where every corner and every face center may have more than one atom. In fact, I know a few crystal structures which are so complicated that every corner has more than 500 atoms. Then I cannot call this as an atom sitting at the corner. So we say a lattice point sitting at the corner. So once you have a lattice with lattice points, now if you add a motif can be 1 atom motif or 100 atom motif or 10 atom motif or 1000 atom motif, and that plus this is what is a crystal structure. And in pure metals, the motif is 1 atom motif. For example, if I take a H2O, H2O is hexagonal. And if I ask this question, for example, if somebody asks a question, how many atoms are there per unit cell in an aluminum FCC? What we say? We say there are 4 atoms per unit cell. Why do we say that? Because each corner, okay, is shared by 8 unit cells. It's not just 1 unit cell. So we say each corner contributes to 1/8 towards that. If I put an atom here, only 1/8 of the atom belongs to this particular unit cell, rest belongs to the other unit cells. And how many such corners are there? 8 corners are there, and this becomes 1. And there are 6 face centers. Each face center, half of this face center atom comes to this unit cell, rest of the half goes out. So it is 1/2 into 6 such planes, it becomes 3. So it is 4. I can say there are 4 atoms per unit cell. I cannot use the same argument for hexagonal. If I do the same thing for hexagonal, normally in a hexagonal, if I do it, I get 2 lattice points per unit cell. We do not say 4 atoms actually, we say 4 lattice points. For a pure metal, 4 atoms is okay, not for every structure. And when I say hexagonal has 2 lattice points per unit cell, whereas at each of the lattice point, if I put H2O there, at each of the lattice point, if I put magnesium atom there, in magnesium, you know, there are certain structures, certain elements such as magnesium, titanium, zirconium, these are all hexagonal. If I put that, then we say there are 2 lattice points per unit cell. Whereas if I put H2O there, then you see at each of the lattice point there are 3 atoms. In principle, it is 6 atoms per unit cell. Though it is 2 lattice points, but the number of atoms wise, it is 6 atoms, because at each of the corner there is H2O sitting, not H or O. It is sitting as together as one molecule. So whenever we are talking about such structures where you have a molecule sitting at each of the corner, you need to say that we can only talk in terms of number of lattice points. If you want to talk about number of atoms, it is the number of atoms inside the molecules multiplied by the total number of lattice points per unit cell. You have to consider that. So this has to be kept in mind. So whenever we are talking about unit cells. Now, so as a result, if somebody asks you a question, how many such unit cells are possible? Then we can say that there is a primitive unit cell, there is a body centered, there is a face centered. I can forget about the word cubic for the time being. Okay, I can call say a simple body centered, face centered, and I can also have what is called base centered. What is the meaning of base centered? Base centered means a unit cell where you have no lattice points on the faces other than the bottom base and the top base. You may say, sir, why do I call the top one also as a base? It all depends on how you look at it. Okay, I can treat this as a base. I can also treat this as a base because I am talking about a whole crystal structure with all these unit cells extended in all the 3 directions. So I call this as a base. The bottom or top, depending on where you put your origin, this can be a base, this can be a base, or something else can be a base, something else can be a base. So I can talk about base. So if I say this, then in principle there can be 4 unit cells in each crystal system. So if I say 4 into 7 crystal system, I should get 28 unit cells. But we know pretty well that there are not 28 unit cells, but what we have is only 14 brevi lattices. 14 unit cells only. They are called 14 brevi lattices. This is the person who has worked on it, so that's why we use that. Then the question is, why is that? So why we have only 14, why not 28? This question can come to anybody's mind. So for example, let us take a few examples and say why it is not so. For example, if I take a cubic, in a cubic you have only a simple cubic, a face-centered cubic, and a body-centered cubic. You don't have a base-centered cubic. Why a base-centered cubic is not possible? Why it does not exist at all? The reason is, once I talk about a cube is one where all these are equal and all the angles are equal. Then if all are equal, depending on which direction I see, it is very difficult for me to define what is base, because all of them are equal. A cube, from any direction you look, looks like a cube. Whereas a tetragonal is not like that. Tetragonal definitely has a base. Hexagonal definitely has a base. Orthorhombic definitely has a base, because all of them are not equal. Because all of them are equal, the moment I put an atom here and here, a lattice point here and here, automatically, if I look at from this direction, this becomes a base. So I have to put a lattice point here. If I look at from this side, this becomes a base, and I have to put an atom there. Then it automatically becomes a face-centered cubic. So body-centered cubic is, base-centered cubic is not possible, because cube has a particular symmetry, which is a equal symmetry in all directions. Because of that, you cannot have a base-centered cubic. Base-centered cubic is not possible. Now if I look at tetragonal, what are the unit cells possible? We know there is a simple tetragonal, there is a body-centered tetragonal. Is there a face-centered tetragonal? Is there a base-centered tetragonal? No. These two do not exist. Why is that so? Let me try to explain you this. For example, let's take a tetragonal and think of a base-centered tetragonal. And to understand this easily, I will extend this once again. Take 2 unit cells of base-centered tetragonal. And I have a lattice point here and here. This is a base. Of course, there are also lattice points at the corners, atoms at the corners. And if I join this with this and join this, Now I get a unit cell. What kind of a unit cell is this? This is also a tetragonal unit cell because this is equal to this, but not equal to this. That means this is also A equal to B, but not equal to C. What about the angles? This angle is 90, this angle is 90, and this angle is also 90. All the angles are 90. Alpha equal to beta equal to gamma equal to 90 degrees. So what is this unit cell? Is it a tetragonal? Yes, it is tetragonal because A equal to B but not equal to C. And all the angles are equal. So it is a tetragonal. But what kind of a tetragonal it is? Is it a simple tetragonal? Is it a body-centered tetragonal? Is it a face-centered tetragonal? If I carefully look at it, it is actually a simple tetragonal. That means a base-centered tetragonal can be visualized as a simple tetragonal. Now the question is, if atoms are arranged as a base-centered tetragonal, should I call it as base-centered or simple tetragonal? That is the question that will arise. That is where crystallographer said, when a question of what to choose comes into picture, then there are certain things to be looked at. For example, to understand this, let us go to 2D. Let's say I have atoms arranged like this. This is the atomic arrangement in 2D, let us say. I want to know what is the unit cell that describes this 2D arrangement atoms. I can say this is a unit cell. Somebody may say, no, that is not the unit cell, but this is the unit cell. Somebody may say, no, why should I choose that as the unit cell? I will choose this as the unit cell. And somebody may say, no, I will choose this whole thing as the unit cell. Then what is the choice? How do I choose it? That's where there are certain criteria. First criteria is the symmetry. You should choose a unit cell which has the highest symmetry. Now what is the highest symmetry? In 2D, it is only a square that has the highest symmetry. Rectangle cannot have a higher symmetry because rectangle has only a two-fold symmetry. A square has a four-fold symmetry. And this is a kind of a rhombus. A rhombus does not have a two-fold symmetry or a four-fold symmetry, so rhombus cannot be higher. So I will, if I have to choose between this and this and this, which is a rectangle, I would choose this. That is because it has the highest symmetry. Now you may say, sir, this is also a square. This is also a square. What do I choose? Both will have the same symmetry, right? So both are cubic, so both will have the same symmetry. Then the next question comes, okay? The next choice will be the unit cell with less number of lattice points. This is this. I choose this as the unit cell. Now, if I use this argument, you will see that base-centered tetragonal, when I showed that it can be treated as a simple tetragonal, base-centered tetragonal has how many lattice points? If I calculate, you will see once again, if I draw this base-centered tetragonal, if this is a base-centered tetragonal, how many lattice points? It has 8 corners. So 1 by 8 into 8, this is 1, and 1 top and bottom. So half into 2, this is 1. So total is 2. 2 lattice points per unit cell. Now if I can treat the same thing as simple tetragonal, then the simple tetragonal will have how many lattice points? It will have only 1 lattice point. So I cannot call this as a base-centered tetragonal. I should call it as a simple tetragonal. So base-centered tetragonal does not exist. Similarly, if I take a face-centered tetragonal and do this, for example, if I extend this, now I say it is a face-centered tetragonal, let us say. That means it has atoms here, and everywhere. Okay, let's not confuse with so many, but I will only do exactly the same way I have done earlier. I will join these fellows. You may say, sir, why are you joining like this? It is because in any atomic arrangement, these lines are not there inside the atoms. Atoms are there arranged. Lines I am joining to understand a particular building block. So the lines are drawn by me to understand. So I can draw the lines like this, or draw the lines like this. It is my choice. So to find out what is the building block. So if I want to understand this, now what is this new unit cell? It is a body-centered tetragonal. Because there is an atom here or a lattice point here. Now, so an FCT can be visualized as a BCT. And a BCT has how many lattice points? 2. An FCC has 4. So an FCT does not exist. Because it has the same symmetry as tetragonal. All tetragonals will have same symmetry, 1 4-fold. But this has less number of lattice points, this has more number of lattice points, so FCT does not exist. So tetragonal, if I say tetragonal has simple tetragonal and body-centered tetragonal. That's it. Like this I can prove in principle why only 14 are there, why all of them are missing. Rest of the 14 are missing. Otherwise, in principle, 4 into 7, we should have 28. So you see, there are no 28. That's the reason. And now, I can also ask you the same question. If I have an FCC, using the same argument, I just now said FCT can be called as a BCT. Can I not take an FCC, this is an FCC, and join these? Now, what is this unit cell? Originally, this was an FCC. Now, if I join like this, I have a unit cell where this is equal to this, but it is not equal to this. Why? Because this is root 2a by 2. This is a by root 2. This distance is a by root 2. This is also a by root 2 because this is face diagonal by 2. So this is equal to this. But what is this? This is equal to a. Because in cubic, a equal to b equal to c. So this is a. So that means this is a in the new unit cell, a equal to b, which is equal to root 2a by 2 or a by root 2, and c is equal to a. That means what? This is a tetragonal unit cell now. And all the angles are 90 degrees. So now I am looking at not the cube, I am looking at as a tetragonal. And what kind of a tetragonal is this? Because there is a face here with a lattice point sitting at the center of it, it is a BCT. So FCC can be looked at as a BCT. Now why can't we call all FCCs as BCTs? The reason is symmetry. An FCC has a cubic symmetry, has a higher symmetry. A BCT has a lower symmetry. I cannot call an FCC as a BCT because it has a lower symmetry. And this is the reason why when people talk about, austenite to martensite transformation, that is when an FCC goes to a BCT. And it happens why? It happens because of a shear. The shear makes the FCC into a BCT. Otherwise not. Otherwise it is only FCC. I cannot, though I can connect it in this fashion and call it as a BCT, I would not call it as a BCT because BCT has a lower symmetry. So this is how we have to understand the unit cells and how the 14 Bravais lattices have come instead of the 28. And what are the other important things that I need to know whenever I say a unit cell? We should know a few other things. One is the number of lattice points. The number of lattice points, if I simply talk of a few important unit cells for us, for example, if I say BCC and FCC, let's say HCP, let's say. In hexagonal also, please remember, there is a hexagonal and hexagonal close packed. I think some of you possibly already know this. When I say hexagonal, hexagonal has only a layer, atoms arranged like this in one layer and another set of atoms arranged like that in the bottom layer. It's just layers and layers of atoms. This is what is actually graphite. And that is what now people are doing. If you look at this graphite, graphite is nothing but another layer like this, atoms, which are, and if I join all of them, this is what is a hexagonal. And with layers of atoms. This is called a layer, this is called another A layer. And within this layer, atoms are covalently bonded. Very strong bonding inside this. But between these two layers, you have a very weak van der Waals bond. And that is the reason why you know that a graphite is very soft. We use it as pencil leads. Okay, it shears very easily. Graphite is also used as a lubricant in many powder metallurgy components. The reason is it is very soft because the bond between any two A layers is very weak. In fact, now what people are doing is they are taking out each of this layer. If you can peel off each of this layer, and I simply have a sheet of graphite, and that sheet of graphite has covalently bonded atoms, and that is what is called graphene now. A lot of people are talking about this graphene because it's very strong sheet. Inside the sheet, you have covalently bonded carbon atom. Now if I take the sheet, roll it, make a tube out of it, that's what is carbon nanotube. And carbon nanotube is nothing but that covalently bonded graphite sheet which is rolled to make a tube out of it. So that on the tube, on the surface, you have all covalently bonded. And that's the reason why the carbon nanotubes have very high strength, high modulus. In fact, it has a Guinness Book of World Record that its modulus is 1250 gigapascal. The highest Young's modulus that anybody has seen so far in any material is this. In comparison, a steel will have 200 gigapascal. So that's the kind of modulus that a carbon nanotubes have. So you can have this kind of layer. But instead, if I have another layer of atoms in the middle of these two A layers and call this as a B layer, such that I have an atom sitting at, if I have atoms touching each other, if I have atoms touching each other in a hexagonal fashion, I see I have voids here, 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 right? 6 voids. And if I can choose to put an atom at this and at this and at this, at the alternate voids as centers, then you see a second layer. That is called a B layer. And if I again put 6 more set of atoms on top of it, 7 atoms to be exact, 1 atom at the center, 6 surrounding it, that is called another A layer. So you call it as AB, AB, AB stacking. This is what is hexagonal close packed. If it is only hexagonal, it is only A stacking. So that is hexagonal and hexagonal close pack. Most of our metals fall as hexagonal close pack. Certain special materials such as graphite, and they fall as hexagonal. So if I look at this and I see that the number of lattice points, if I look at it, a BCC has 2, an FCC has 4, and a HCP has 2. In fact, many people say HCP actually has 6. If you read some of the textbooks, they say 6. But the problem with that is we do not consider this whole prism as a unit cell for a hexagonal. The unit cell in a hexagonal is only this part. This part and this part and joined together. Okay, and this is joined here. Okay, so we don't bother about this. So this is the one which is the one. So this joined like this and this is joined to the bottom part. This is only the unit cell. But if I look at only this unit cell, I will not be able to see the hexagonal symmetry easily, the 6-fold symmetry easily. That's why people show this whole block, whole prism as the for understanding, but the actual unit cell is this. So that means this hexagonal prism is composed of 3 unit cells. This is one unit cell, this is another unit cell, and this is another unit cell. Brought down together and then joined. And if you look at each of these unit cell, it has only 2. Otherwise, if you consider the whole prism, it is 6. But it is only 2. And similarly, if I talk about coordination number of nearest neighbors, you can see in a BCC, you have 8. You can say in FCC, you have 12. And in a HCP, again, you have 12. And if somebody tries to calculate the packing fraction is number of the volume of the unit cell occupied by the atoms. You will see in a BCC it is 0.68 and it is 0.74 and it is again 0.74. That's why if you carefully look at it, this HCP and FCC have similar packing. It has similar coordination number, similar packing. They are very close packed when compared to this. That is the reason why whenever I want to use a material for high temperature application, for creep application, for high creep resistance, we always use only FCC. Why? Whenever you have close packing, atoms cannot diffuse easily. At high temperature, one of the ways by which material deforms by creep is by atomic diffusion. If I can somehow prevent atomic diffusion, then materials does not deform easily. So if I can choose, that's why all the superalloys that we talk about, nickel-based superalloy, iron-based superalloy, cobalt-based superalloy, they are all used only as FCCs. We do not use them as BCC. There is no BCC superalloy. Always FCC is used as a superalloy. So that's how you see crystal structure plays a very important role. Similarly, for low temperature applications also. For example, if I want to use something for a cryogenic application, if you want to make a tube where low temperature ice water goes through, then you again use FCC because FCC has very high toughness. The ductile brittle transition temperature of FCC is very low. And because you can easily deform FCC, the ductility and the toughness of FCC is very high. So for both low temperature application and high temperature application, it is always an FCC structure. That's why. So it's very important to know about crystal structures. So crystal structures can play a very important role both in defining their high temperature deformation behavior and also low temperature deformation behavior. One has to be very careful. So these are all certain important things to know about the unit cells, various parameters. For example, one also important thing that to know is, for example, if you want to find out the packing factor. Packing factor, if you want to find out, there are certain relations that you need to know. What is the packing factor? Packing factor is that the volume occupied by atoms divided by the volume of unit cell. If I want to do this for BCC, for example, what I need to know is the volume of the unit cell. Volume of the unit cell in BCC is A cube. Right? A into A into A. That is the volume. But I need to know what is the volume occupied by the atoms. How many atoms are there in a BCC unit cell? There are 2 atoms. Right? What is the volume of the atom? Volume of the atom I know is as 4/3 pi r cube. Is the, because atom I am assuming it to be spherical. But this is an atomic radius. This is the lattice parameter. I need to know the relation between these two. Unless I know the relation between these two, I cannot know what is this factor. So to know the relation between these two, I have to draw the unit cell and put an atom at the body center and atoms at the corners. And if I look at now the relation between R and A, you know that if I look at this body diagonal, and draw that body diagonal here, you will see an atom is there at the center, because this body center atom is at the center of the body diagonal, and you also have an atom at the corner. If I say these are the 2 corners, and this is, of course, they are all equal in size. Please excuse me for that. So if I take this, then this is 1 R, this is 2 R, this is another R. So this total length is equal to 4R. So 4R is equal to, what is the body diagonal? Body diagonal is nothing but √3A. I think all of you know this. So that means this is the relation between the R and A. If I use that relation here, I will find that this value is 0.68. So that means the relation between R and A is, for BCC, is 4R equal to √3A. If I do the same thing here, the relation is 4R equal to √2A for FCC. And similarly, I can do this. In case of HCP, there is a special relation between C by A is 1.633. In case of hexagonal closed packed, that can be proven, and that is how these are various parameters. I think with this, we will stop and take up how to look at various planes in these unit cells in the next class. Okay, we'll start.